This is me, Totality. How are you all doing? So, this has been overall a great journey from my chemistry to end. If you don't know what my previous challenge was, say hi to my 75 Ultra Hard bottles. If you don't know, this was the main one to give me the first challenge. And by looking at this, you'll get to know that there are a bunch of challenges inside. There are many, many, many of them. Each and every cheat is written by some of my friends, and yeah, there are many of them. If you can look at this, these all cheats, I have to try my best to complete each and every one of them. That's why this challenge is known as 75 Ultra Hard. 75 Ultra Hard. Now, what exactly am I gonna do here? I'm going through some small parts of the chapter, and yes, it's not gonna be easy at all. um, I'm just gonna wait for some viewers to pop up and then we're gonna open this because it will kill the vibe, it will not, it will kill the hype. So I just want to build up some hype. I'm kind of excited too because it could be anything random. There's a probability of anything to be popping up. I don't know, there are some very crazy, weird challenges that could be there in this. So yeah, whenever I try my best, I hope I do not get any kind of quirky, weird thing. If I get any of that, then it's gonna be very crazy, dude. Very, very crazy. So yeah. Oh, I accidentally saw one. It's some one chat is kind of open, but yeah, I didn't get to know what it was exactly. It's a bit open, but I didn't see it. It's fine though, it's not that big deal of a problem and working a bit here. Anyways, what do I need to do next? Oh, that just fell off from the point. Okay, so let's say that I'm starting from a point of here. Then I will put up my book at this side. Okay, let's say that I'm doing it at this point, and I said that, oh yeah, I fell through this point. I went through that moment. So that's how I'll get to know about what all things I have done overall in chemistry. And yeah, some random people told me about this, and they said that this bottle has, like, many random challenges. So any challenge can pop up from this bottle. And if I started, I'm just opening it right now because that's the moment for me to do it. So I'm just waiting for viewers to pop up so that it does not kill the vibe, it does not kill the hype, or else it could be, a wrong timing. So this bottle right here has many, many challenges inside it. And I'm gonna open one of them today and see what exactly the challenge will be. Bro, the first shit I opened was a long challenge. I don't want to be a very big challenge, by the way. Once we open this, we're gonna do this. We're gonna start the challenge tomorrow. So this is just to check out what are we gonna do. So let's shake this up. We're shaking up. Okay. Okay. And by shaking this in, and we're gonna open this. Okay, I'm gonna open the cap. Okay. In three, two, one. Okay, let's go. Please don't give me a bad one. You have to do this tomorrow. This challenge. This is the shit that popped up. This is the shit. Okay. Whew. And by the way, if you don't know, these all are written by my friends, so I have no idea. Some of them I might have some. Okay. Oh, we got one challenge here. Derivations of laws of motion. So I gotta do all the derivations of laws of motion, which means that's a short challenge. I can complete this under 1 day. So we got to have our full completion of all the derivations of laws of motion. Like, I literally looked at this. Can I just show it to you? Derivations of laws of motion. I'm not sure whether the image is inverted or not, but it says all the derivations of laws of motion. I don't know how many derivations are there. Let's count. Law of conservation of momentum. Then we have friction, the acceleration down to that slope, or work done to that slope. Then that's three. Then we have flat. There's level road and banked road. Five, and then we got what else? What else did we get? Oh, this is gonna be so cooked. Okay, so then we got fifth, and then the sixth and seventh one. What is it? I remember it's. I think the angle of angle of friction, angle of repose, then bending of his angle list. I have no idea. I will not include that derivation. I feel it's not much important. It's not much of that, really big importance. But yeah, so there are more than seven derivations as far as I know. Um, I don't know exactly, but yeah, there are many derivations for that chapter. So we got ourselves a small challenge in this chat, and that's a pretty good one, bro. This is interesting. We got one nice one. We got a nice one right there. And yeah, it's a good challenge. Thank you to anyone who actually gave me this challenge. But bro, this is gonna be lit. So let's complete our full long-term challenge first, and then we'll move on to a bigger one. It's gonna be so fun. It's gonna be super good. Like bro, this was the one. And as you move on, I'll be completing all these ones in 75 days, because some are really big challenges, some are really short challenges, and some are mid, like I can complete them in 3 days. That's how it is. So yeah, the challenge that I got previously was to complete full chemistry, which was a long challenge. And yeah, I'm at the last chapter, but this is the moment for me to start another challenge for tomorrow, and I opened it today. So that's what I did today here. So this is the one shit. The shit I got was again, they all do all the derivations of laws of motion. So Newton's laws of motion. There are three laws of motion, and it is based on the branch of mechanics of physics, dynamics. So based on that, that is friction and momentum, and related to other ones. Oh yeah, the second law of motion. So there's more than eight derivations I have to do. Eight derivations. What are derivations? It's basically to show the proof or the evidences to find or make formulas that we know overall. Like I don't know. There are many formulas to know. Like m1u1 plus m2u2 is equal to m1v1 plus m2v2, law of conservation of momentum. F is equal to ma, Newton's second law of motion. Then you got angle of repose, angle of friction, which is equal to which are both equal if you don't know. We have to show that derivation. Then we got our acceleration. A is equal to g into sine theta minus mu cos theta if it is moving down the slope. If the work done is done upwards on the slope, then it's gonna be w is equal to mgs sine theta, mgs into sine theta plus mu cos theta. Many different versions. There are many types. So we have to do this one such kind of thingy in this one. What was that? Let me just show you. Opera Puka. Hi Kotijo Nakuti 8865. I did not understand what you're trying to say, but thank you very much for the message. I think you said something illegal. I have no idea, but it's fine, I guess. I'm just gonna hide that for now, because I think that message could be a bit, weird. I have no idea what you're trying to say. If you can say it in a more understandable way, it's fine. It's legal. Okay, my bad, my bad. How are you doing, Kotijo? I'm not sure. My bad for pronouncing. Kotijo Nakuti 8865. Okay, but then it's Europe says that it is held for Viviv. I don't know. Well, I'll show it to you. Okay. Okay, now it's fine. Now it's fine, guys. Now it's fine. I hope you can see the things and messages. So, let's say that I want to. Yeah. So basically, if you don't know what I exactly did, is that I actually took of these one shit out of these challenges, and I got the challenge as I'm just gonna show it to you. I got the challenge as I have to do all the derivations of laws of motion. There are overall like 8 to 10 derivations, and I gotta do that. More than 8 derivations, that's for sure. I know. Yeah, it's more than eight, as far as I know. So yeah, I gotta like do that, and we gotta move on. Actually, that's how we are gonna do it, or else we are cooked. So how are you all doing? Like, I'm gonna put a Q&A here. How are you guys doing? Doing? I'm just gonna put this up, put a really good one. Okay, right there, and put that up. Done. Yep. Start the Q&A. That's how it is. So, overall, that's it, I guess. For tomorrow, I'll be completing this challenge, and I'm gonna open another one. I'll be opening all these challenges one by one. The long ones will take a lot of time, but the short ones will take only one day. So that's not much of a big problem for me. But yeah, here we go. We are getting some really good ones here, finally, and I'm happy for that. Anyways, let's complete the lengthiest challenge I got so far. That is completing full chemistry. I have to complete full of the chemistry, and as you can see, I'm doing that right now. I'll just show it to you. I'm completing this full chemistry right here. Like I'm at this conceptual part of the chapter. You can literally look at what I'm doing. Like literally look at this, dude. Look at this. Then, yeah, I completed organic chemistry. You can just ignore this one. I completed this part. I'm doing, this electrochemical cell right here. You know what? I'm gonna remove this for now. Yeah, I'm just gonna remove this. You can really look at this. That's how it is, man. That's how it is. Then I was doing a lots of some of these reactions are wrong. The balancing is not correct, but I tried my best to make it better and correct here. Like literally look at the reactions I've done, man. I had to balance all these reactions and do all those stuff. Like yeah, that was a bit complex one right here, not gonna lie. Took me a lot of time to balance these, but it was fun doing those, not gonna lie, these questions that we were doing, those were fun, not gonna lie. Look at those, like that's how have been doing. Yeah, anyways, let's move on. I do not want to waste my time. So basically, I started off with learning that there is an electrochemical cell. It's a spontaneous reaction. What we need to know is that whenever the dissociation takes place, here a zinc sulfate solution, the Zn2 plus is formed and sulfate 2 minus ions are formed. In oxid, this part here is having the electrode as anode, and this one has cathode. The anode is in contact with the this part of this vessel that is taking place, that only oxidation reaction is taking place here. The only reaction to be taking place here is reduction reaction, so we are calling this as OHR and RHR, that is oxidation half reaction and reduction half reaction. In oxidation half reaction, hi Aquaman 2612, hi, how are you doing? How are you, man? Nice to meet you, by the way. I appreciate your comment. So, if anyone wants to talk, you can talk. I will read your messages. I'll respond. I know. Well, I'm just going through this concept, and I can also understand if you want to. And by the way, there is a Danielson that is consisting of copper and zinc. Here, the zinc gets loses their electrons. So, well, it loses the electron that is negative in nature. It becomes positive. So Zn2 plus here, which means that it's like removing negativity from your life makes you positive. That's what the zinc is doing. In oxidation reaction, it's removing those electrons which are negative in nature, and it becomes positive. So it's removing two electrons and becomes positive twice. So 2 Zn2 plus. That's how we get to know that these electrons that are removed are transported to this kind of electrode, anode, and then this moves out throughout this reaction, and this it comes through this cathode electrode. Then, hi Aquaman 2612, I can read your messages. What happens after this is that here the electrons are released. After here coming from here, the electrons are released. Now what happens in this is that the electrons that are released will combine with the copper 2 plus ion to form the copper solid form, and this copper solid form deposits along the electrode. Here you can see on the cathode. This is a zinc rod, by the way, if you don't know. So this zinc rod loses the electron to become Zn2 plus, and we already know that Zn2 plus gets dissociated from the zinc sulfate ion too, and Zn2 plus is formed when the electron transports from here to here, and losing electrons on the zinc rod, that is Zn2 plus. So the Zn2 plus ion becomes very very concentrated, and since it becomes very concentrated, it can lead to the blockage of the electricity, that is for the electrons to go through this, or for the reaction to take place. And that's why, in order to not happen this, we have this thingy, and this thingy is known as salt bridge. This salt bridge consists of inert electrolytes or chemical species which are capable of solving the electricity problems here. Like, it maintains the electrical neutrality. The inert electrolytes or the chemical species that we see is potassium chloride or an ammonium nitrate, NH4 NO3. This will be put along with the agar gel. The agar gel that you see is basically obtained from the hydrocolloids from Phaeophyceae or the brown algae. That is related to a bit of biology topic, but yeah, those are agar gel that is combined with the KCl. And here, let's say that you could plug two cottons on both the sides. When you plug two cottons on both the sides of the U-tube, you're basically balancing the concentration on both the vessels, and that's how you're maintaining the electrical neutrality, and you're helping the electricity to be passed down. And remember that in normal electricity current direction, it is always opposite to the conventional direction of electrons. So if electrons are moving from this direction to here, the current will flow from here to here, which means that it is opposite. Now current can be less than 1 ampere, I feel, because it's in very small amounts. As you can see, we also put a galvanometer. This galvanometer measures the current overall. That's how we get to know. Now if we try to look at this is a bit complex to understand because it requires a higher level of chemistry understanding. Here the Zn is releasing electrons, so it's gonna release electrons and becomes positive. Here this copper here, the electrons will get transported from here to here, from this side to this side, and here the Cu2 plus ions will combine with the two electrons to form copper solid, and this copper will get deposited on this electrode here, as you can see. And overall, if you look at this, we can cut these two electrons to get the net reaction as Zn solid plus Cu2 plus aqueous. This aqueous represents that this ion is mixed with water. That's what it says. And solid means, it's very rigid. Like your pen here, you can see that it's very rigid. Is it like breakable? Can you easily break it? It's a bit difficult to break because, it's very solid. It's rigid. It's very tough. But like your water is a liquid, right? So you can actually change its shape, volume, and all that stuff. So you write it as a liquid. Or your oxygen, which is a gas, you cannot see through it, but you know that you're breathing oxygen in and releasing carbon dioxide. Similarly, there's another state that is aqueous, where the solutions are formed from this, that you're mixing something with water and that becomes aqueous. So this is for the ions. Overall, after the redox reaction, that is both reduction and oxidation reactions taking place to form Zn2 plus and Cu solid. Now, if you look at this cell representation, we can write it in the form of this, and this is known as zinc solid, which is forming Zn2 plus ions through the help of anode, and it is represented by a straight vertical line. Now, these two straight vertical lines you see here, which are parallel to each other, they represent the salt bridge. And this one here, Cu2 plus being formed to Cu, this shows that there is cathode involved here as a straight vertical line. This is the cell representation. Now, this whole concept that we see here, we studied this in 12th standard chemistry known as electrochemistry, where it is very much easier to understand. We also understand the voltage, which is, the potential difference of the circuit, overall circuit. Now let's understand this thing. What exactly does this thing do? What is this salt bridge? What exactly does the salt bridge do here? What exactly is the function of salt bridge over on this kind of method, or on this kind of reaction taking place? If you look at it, it says it completes the circuit by allowing the flow of electrons. What exactly happens is that electrons move from here to here to here, then the reaction takes place here, also the reaction takes place. That's how the reaction is overall happening. But sometimes the circuit has to be completed, and salt bridge is used in order to show that electrons to be flown from here to here back, and that's how the circuit is complete. It also helps in maintaining electrical neutrality. The problem here with that is that sometimes that Zn2 plus can be dissociated from zinc sulfate. I can show you that reaction right here. The zinc sulfate reaction is basically giving us a dissociation. Now, I'm not sure whether this is a strong salt or something, but let's see. This gives you Zn2 plus ion plus SO4 2 minus ion. Now, this Zn2 plus ion is aqueous, and this Zn2 plus ion. Look at this. This a cathode, this anode consists of zinc rod, and this forms Zn2 plus 2 electrons released. So Zn2 plus here, Zn2 plus here. Now we can see that the Zn2 plus ion has a really large concentration, and this large concentration present here can lead to the blockage of the electricity here, and this electricity to be stopped, or sorry, not to be stopped and to be continued, this salt bridge is required, and this salt bridge helps in maintaining that. That's how it is done. And yeah, that's how you actually see the continuity of electricity here. And overall, if you look at this, we have the two ends of salt bridge, uh not this one, my bad. We have another thing called standard hydrogen potential, or I call it as SHE. Now, She consists of platinum electrode. This platinum, which is an element Pt, and I think you may know it. It's very difficult to find it out. It's very expensive too. It is coated with a layer of platinum black. This is platinum black, and it is kept in 1 molar HCl solution. This is your 1 molar HCl solution surrounding the platinum black. As you can see, and let's say that you're pumping in the H2 gas at 1 bar. 1 bar is basically overall, I feel, 1 Pascal. As no, sorry, 10 raised to 5 Pascal, not 1 Pascal, 10 raised to 5 Pascal. And 298 Kelvin is the temperature, that is in 25 degrees Celsius. Or if you try calculating in Fahrenheit, it's gonna give a bit, normal Fahrenheit, which is a bit cold. I mean, it's fine though. It's at room temperature. So room temperature Fahrenheit can be seen, or Fahrenheit can be seen. And looking at this, the two electrodes potentials are can be done experimentally. So the thing is that it cannot be exactly measured directly to get the single electrode potential. So we use the reference to measure the difference between these electrode potentials, and that's how we overall get this. The reference electrode is used to actually show the indirect measurement of the potential of electrode, and that's how we get it. We use the galvanometer experimentally to get the value, and then we already know the reference electrode's value, and we subtract it with the galvanometer value to get the overall electrode potential value that we know. So that's how indirect measurement is done. Now let's talk about redox couple. What exactly is redox couple? Now, I think we're close enough to complete this chapter, and that's it. Yeah, that's it, I guess. It's just after that we have this, which is not much important. Oh yeah, we're gonna complete this, guys. Just wait for a minute. It's gonna take some time, but that's it. It was a bit weird. So let's understand this. Okay. Now it is defined as having together the oxidized and reduced form of the structure. Let's say that you put a oxidized iron, and you put it in a solution which consists of those substances to be going under oxidation or reduction. That's how it is actually. So let's say that you put a zinc rod, you dip it in Zn2 plus ion, and this one such thing you see, you put an anode, and that anode you see, it's not an anode, my bad, cathode, and that has how it represents like Zn2 plus ions to be seen in Zn. That is interesting. That is how redox couple is done. And electrode potential. The potential difference between the electrode and electrolyte is known as E cell. So it's basically redox couple potential difference. You can see electrode and electrolyte. Now, if the tendency of the electrode is to gain electrons, then it is basically reduction potential. If it has the capability or the tendency to lose electrons, it is an oxidation potential. Oxidation potential mainly we see that electrodes having oxidation potential is basically anode, and cathode is basically our the main reduction potential. Yeah, Zinc in the case of Daniel cell, copper in the case of Daniel cell. Zinc and copper are one such class examples. If you don't know what exactly need to know about Daniel cell, they have zinc and copper require the measurement of the Daniel voltage, and that is satisfied. Then we have standard electrode potential. I know this is very difficult to understand, but this is just a short-term revision to go through each and everything what we have studied overall. Oh, brother, this is so interesting, right? I mean, yeah, this is super, super interesting. I mean, that's how we're gonna go through. So the concentration of all the species involved in a half cell is unity, okay? So we're taking that the concentration involved in this reaction will be unity, and the temperature is at room temperature 298 Kelvin, or let's say 25 degrees Celsius, and then the electrode potential standard. Then the electrode potential will be now referred to as of standard electrode potential. Some people say it as a standard reduction potential at first, but then it's known as standard electrode potential because it's better off to say that, as it also requires oxidation. Arrangement of various elements of decreasing order of their reduction potential is called as an electrochemical species. So, what exactly do we need to know? We need to know that the more negative the electrode potential value becomes, the more reducing capacity it has. So, let's say that if it has a negative value, the redox couple is basically a stronger reducing reagent than H plus 2 H2 couple, that is SHE. And if we talk about the positive E naught value, the redox couple is a weaker reducing agent than H plus H2 couple. That is just showing that it's just a weaker reducing agent. It may have the capability to even oxidize sometimes because of that very weak reducing agent capacity. So I mean, sorry, am I saying something wrong? Oh, yep, I said something wrong. Oh my god, bro. Okay, never mind. I get it. So calculation of E naught cell. If we take the E naught cell of this one, E naught cell of this one, we do the calculation and we get the value. This is the E naught cell value of the Daniel cell. This is the Daniel cell E naught cell value. If it is positive, the reaction will be spontaneous. That is the favored, and only for the E naught cell. If you But we know that if Gibbs free energy is negative, it's spontaneous. If Gibbs free energy is positive, it's non-spontaneous. And it's seen at all temperatures, at high temperatures, or even at low temperatures. That's thermodynamics. And E naught cell is zero, then system is in equilibrium. E naught cell negative, the reaction is non-spontaneous. That's the one main assurance of the thingy. And predicting the feasibility of redox reaction, that is one such thing we need to know. Now that's yeah, you can see that cathode is reduction, following reduction, anode is following oxidation, and overall we see that the more negative it is, the more reducing capacity, and that's the end of the chapter. I know, but it's just a revision. I explained it super badly. No one can understand like this, but it's just for revision purposes. Revision purpose helps us just to go through the things once again. So I have revised it a lot, so I have a lot of ideas. I'm saying this because and now I get the ideas of what I'm going through. But yes, that's how it is, man. That's how it is, bro. That's how it is, mate. And yep, it is how it is. I look fully stressed out. I don't know why. I'm fine. I'm normal. I'm normal. What am I doing? Oh, what am I doing? Oh my god. What am I doing? Anyways, I think that's it for now. I'll just go now. That's fine. I gotta go. Allah Hafiz. Bye. Where is that shit, dude? Where is that shit? Chitty chitty chat. I'll do this challenge tomorrow because um I thought it's very late at night and I have to complete this previous challenge. There's still some part left, and once that's done, it's done. That's it. So yep, I gotta go now. Till then, soon enough. Bye. Allah Hafiz.